So you're able to see my whiteboard, am I right?
Yes, sir. Yes.
So what we are saying is, there is this curve.
Yes, sir.
And there is a curve where the slope is like this. I said that let the threshold voltage be 400 millivolts. This is, let us say, 60 millivolts per decade. This is, let us say, 100 millivolts per decade. Now,
Yes,
I am at, let us say, 340. My gate is at 340 millivolts.
Yes, sir.
What is the leakage for the first curve? If
340
is I, then the leakage over here is I by 10.
Yes, sir.
What about here? Leakage for the other curve? It could be I by 2.
Yes, sir.
You see? So a steep slope means reduced leakage.
Okay. Sir, matlab, I'm like, even I have read this in Razavi, sir. He has given this on basis of power, sir. And like, that's the reason why I've raised the issue. That's it. I mean, I do understand what you are explaining, but yeah. So it's mentioned as such in Razavi. That's it.
So Vaishnav, we discussed this even in the office hours. There could be 10,000 ways to confuse yourself. I am trying to give you one simple way to clarify that understanding.
Yes, sir. Yes, sir. I do understand. Yes, sir. Thank you, sir.
Yeah.
Sir, I have a doubt in this only.
Yes, Agandi.
Sir, when we are talking about 60 millivolt per decade, so I am saying that the 10 times current would appear as I change 60 millivolt, right? But sir, if we start from the same starting point, if I am saying that the curve is starting from origin itself, so
Sorry?
we have to shift. Sir, if the curve is starting from origin,
What is the origin over here? This is a logarithmic scale. See, this is a logarithmic scale. So what is an origin? Is there anything which has the value of 0 except 1? Matlab 1 hoga to alag baat hai. But what is origin over here? Okay, let us look at it differently. How do you think, or in how many ways do you think VT is defined? Threshold voltage of a device. How many ways it can be defined? And which is the most commonly used definition by the industry?
When the inversion layer is formed, then we say that.
Okay. So Gagandeep says, in the last class we discussed that when the inversion layer is formed, so when the band bending happens such that it is equal to 2 phi, and phi, that is when we say VT is there. Okay, what else? That is one definition of VT. So one definition of VT is that band bending is equal to 2 phi. That is when the inversion layer will be formed and we say that the VT has reached. Okay, what else? Now, let us say I have fabricated some silicon devices. I've fabricated some MOSFETs on silicon. I want to identify the VT of those devices. I have to make models so that as circuit designers, you can simulate those models and do some analysis.
Yes, sir.
So how will I, as a technologist, find the band bending in a MOSFET?
Sir, in that case, I will have to fix some current that, okay, this much current if it appears, so I'll say the VT has hit.
Yes. So the one of the very common definition of VT that industry uses is, or that is used is, the voltage at which you have 1 microampere per micron width of current flowing through a device. Okay. So that is where, because VT ki definition is is that unit current. That is where you should consider this as the starting point of your any analysis. For you, this is the origin then, because that is the common point. We said two devices have same VT, but their subthreshold slopes are different. This is what it means. They have same current at VT. Now subthreshold slopes are different. What happens to the current at 340 millivolts? Are you able to see this, Gagandeep?
Right, sir.
So
So, sir, out of 60 and 100 millivolt per decade, then I would want 100 millivolt per decade.
Why? That has more leakage.
Sorry, right. 60 millivolt per decade to be
No,
there on the silicon.
I want as steep a slope as possible. I want as steep a
Yes,
slope
sir.
as possible. Ranjit, you had a question?
Yes, sir. In the same graph, if I say 100 millivolt per decade, this should be the steeper slope, right, sir? Because
Why?
the, del y by del x. So this has larger del y.
No. But where is the millivolts? Is millivolts on X or is millivolts on Y?
Oh, it's on x. Okay. Yeah, got it, sir.
Over here, when we say millivolts per decade, then we are saying del X by del Y.
Okay. Yeah.
So a smaller number is steeper slope.
Okay, sir. Yeah, got it.
so the
So they
standard,
simply keep on confusing you. Nahi, Ranjit?
Yes, sir. Just with the units.
Yeah.
so with you said the standard definition is 1 ampere per what is the unit, sir?
It's one ampere or 1 microampere per micron length. So whatever it is, per micron width. So whatever it is, it's a constant current. That is the definition. That is the thing that you need to take back. As technology advances, that definition, that value of current may also change over time. So don't get bogged down by that. What you need to realize is there are multiple ways to define VT. One is how much band bending has happened. So a device physicist will talk about band bending. But a person who is a practitioner in VLSI would talk about a particular amount of current flowing through a device. And that is the definition of VT there.
Yes, sir. So my doubt was this only. So as we change the technology nodes, that definition will change, right?
No, actually nahi hota hai. From what I know, this definition has remained constant for a very long time. But now that we are entering into extremely scaled technologies with 3D devices and even quantum devices are being explored and piloted, so to say. So it may happen that this definition may no longer be manageable. I don't know. If it works, great. If it doesn't, then we will probably come at some other definition.
Sir, actually, I'm not able to get that. For example, if you move from say 180 to 65 or below, like say 40, then shouldn't the definition change that why it is remaining constant? I'm not able to get it why it remains constant.
No. Why? What is constant?
So why the definition for the VT, the value has remained constant?
Because they're not talking about absolute value of current. They're talking about 1 ampere, let us say, per micron of device, micron width. So if your scaling has happened and the width has reduced, so you expect the current also to reduce. So you will simply, so this is, let us say, a device in 65 nanometer, and let us say this is a device in 45 nanometer. So the width has also reduced and length has also reduced due to scaling. Am I right?
Yes,
so what they are saying is that, okay, width over here has reduced. So we will assume that we will normalize the current value. So this is, if this is I65 and this is I45, then I will look at, and let us say this is W6, yaar kya kar rahe? Let us say this is W65 and this is W45. So I will simply look at I65 by W65 and I will look at I45 by W45. So if W has reduced, I will also reduce. So current also reduces with technology. But since you normalize it per micron width, therefore it is not a challenge. But that is where I'm saying, because we are going to complex device topologies, it might not be the most appropriate way or may not be sustainable way to handle it in very advanced technologies. So I do not know. But abhi, for all practical purposes, you can assume that current and constant current per micron width is the definition of VT.
So, but this definition also takes in fact that the scaling is happening or like as you expected, right? The scaling is happening as expected. So, but like you said that in the previous lecture, there was mentioning about the short channel effect. So, won't it interfere here?
Yes.
This definition.
So VT shifts and then you have to recover it. You have to do device engineering so that you recover it. That you anyway have to do, na?
Okay.
You cannot use the same topology of the device as was there in 65 and 45 also. So when you will join some company and you will look at the details of the devices there, you will see that there is so much to it. Matlab, there are extended source and drain regions. There are stressors, PMOS stressors, NMOS stressors, and पता नहीं क्या क्या चीजें ऐड करी जाती हैं टेक्नोलॉजी में ताकि वो VT वापस बढ़ जाए या कंट्रोल में आ जाए, रिड्यूस हो जाए, जो भी, whichever way. So there are many things that are brought into picture so that things are under control.
Okay. Okay. So, but for our purpose, since it's a normalized value, so we consider that.
Yes.
Okay.
Meher?
Yeah, yes, sir. So when you say that we see the amount of current flowing through the device, do you mean from source to drain or like vice versa? Because in case of when we measure current before the cutoff, before VT, the leakage current happens through body and source or body or drain. So I mean, do we have a fixed standard of current flowing through the device?
No, we're only talking about IDS.
IDS.
Yeah.
So sir, so the leakage.
There would be
current
leakages at other
IDS.
places. We're not measuring those. We're saying IDS should be this much.
So before cutoff, when we are saying, I mean, the current which flows before we reach the threshold voltage, then there is no IDS, right? The current is between
Right.
body and source.
That is exactly the subthreshold slope all about, na? What is the subthreshold slope all about? It is about the current that is flowing when VT has not reached yet.
So this
Why
was
is there no IDS? There is IDS.
Right. Okay. Yeah. Okay.
Hai na?
So, sir, how does I'm sorry, this might be going back a little, but how does this happen exactly? If there's a depletion layer, I mean, the inversion layer hasn't formed yet, right? By definition of BT.
Yeah. So go back to the diode equations. You only have a diode there.
Okay. Yeah.
But,
Right.
hai na?
Okay. Okay.
So again, if you remember the basics, you will be able to arrive at all these deductions. Don't worry.
Okay. Right.
Okay. Kadandeep?
Yes, sir. Sir, in the last class, you said that in smaller technologies, channel is already doped so much that you cannot increase the doping further. So, sir, why is that?
Again, to manage the short channel effects. So
Sir,
let us look at it like this. I have, we talked about the rectangular assumption, nahin? That long channel devices, the channel region over here is rectangular in nature.
Yes.
That is a long channel assumption. In short devices, what happens? The source and the drain come closer. In short channel devices, the source and the drain come closer. So you have something like this happening. Now, this has its own depletion layer. This has its own depletion layer. Now, imagine that the doping in the channel region, substrate region is low. What would happen? This depletion region will be larger. So even without application of any voltage, there will be a connected depletion region across the source and the drain. We don't want that. We want that control to be available at the gate. That only when a particular voltage is applied that we start to have a depletion region. Otherwise, VT will go very low and you will have lots of short circuit currents, lots of subthreshold currents. Therefore, you need to increase substrate doping as you go to advanced technologies. Now, you still have to maintain a ratio between doping over here and doping over here to get transistor behavior. So many things come into picture, and all this is VT engineering, which again, I'm not sure if you will do in solid state devices at all. You will probably think of it in Introduction to Nanoelectronics course, INE. So there are halo implants, super halo implants, many different kinds of things which come into picture. Okay. Madhur? Madhur, you have a question?
Yes, sir. Am I audible?
Yeah.
So this
Now you're not audible. Sorry.
so I just need some time to think.
Okay. So this was an interesting topic. We had kind of quickly covered it in the last class. So now we've covered it in much more detail. Any further questions around this topic?
Yeah, sir, one more, if you don't mind. So you said that we have to apply the diode equations when we look at the sub-threshold current.
No.
But
No. The question was that there is depletion layer, then how is the current coming in? That was where I said it's a simple diode. PN junction is there. You just apply the equations of reverse current in PN junction.
So exactly. So the PN junction is there between the substrate and source and substrate and drain. So the so you're saying that the drain to source current will flow through the substrate.
No, there is a depletion layer. Huh?
So, but both of them are N type, and there's a depletion, a charge-free region between.
So wait, Meher, look at it. What is inversion? Inversion is when there is a WD max that we discussed in the office hours also, and then inversion layer forms.
Yeah.
Now what we have said, VT nahi hai. We are lower than VT. Okay. We are lower than VT, but there is a depletion region. So some charge will enter here into the depletion region, and through the depletion region itself go into the drain.
Through the depletion region.
Yeah. Okay. Because there is depletion region.
So, but both drain and source are N type, right?
So what? They have different voltages.
Okay.
That is talking about any current flow, no? There's a different
I had assumed that your DS will be grounded. So okay.
So both drain and source are grounded, then there is zero VDS. No, then there is no current at all.
Naturally. Right.
If it is equipotential, then what is the point of there is no I also, and there is no I on also, and there is no I off also.
Yeah, naturally.
There cannot be any flow of current then.
Right. Okay. Thank you.
So it seems like the depletion of the PN junction and due to the MOS capacitance that we discovered are getting connected, and that is enabling the flow, right?
Yeah, that's the path. Madhur?
So in the reference book, something is written like even if we have a long channel, then also after pinch off there is velocity saturation, and due to this current is.
So Madhur, your voice is not very clear. Would you want to type it out?
So is it clear?
It is better, but yeah, speak.
Okay, yes, sir. So in the reference book, it is written that even in long channel, after the pinch off happens, there is velocity saturation because electric field, I guess because electric field has become too high, because electric field is higher near the drain. So there should be some velocity saturation due to which current is becoming constant. Is
Yeah.
Is that the reason why in long channel also velocity saturation is happening, and due to that only current is
So
becoming?
you were there in the office hours, Madhur?
I guess in the first half or the later half. I don't remember. So for some time I was there.
Yeah. So I have uploaded the recording also, so you can check there once. If there is any pending question, then we can discuss that again.
Okay, sir.
Okay, because we discussed exactly this point as to why velocity saturation happens early in short channel devices and later in long channel devices and so on. We discussed all this there itself. Right?
Yeah, yes, sir. So I understand why that happens, but is it that even in normal long channel device operation also, exactly after pinch off, no matter what we are doing, no matter how much current we are having, if there is a pinch off, then after, beyond pinch off, there is velocity saturation. Is that true?
No, you cannot definitely say that. There may not be velocity saturation just after pinch off also. It depends on the device dimensions.
Okay, sir.
Okay, it depends on the electric field that we're talking about. Okay.
Okay, sir.
Great.
So I still don't get then why is the current becoming constant after because there is no inversion layer, and so are the collisions becoming is the collision increasing too much or something like that?
So I would say these are all models. I would just repeat that. Okay, we are observing something and we have built models around all of that. Okay, these models will break somewhere. Don't get too attached to these models.
Okay, sir.
Okay, the current saturates because as you, even if you further increase the what do you say, gate voltage, the sheet of charge, the sheet of charge starts to see that there are that sheet of charge or the density of the electrons tends to get limited by the fact that now they cannot really speed up as much. Could be velocity saturation, or because there are more collisions and so on. Okay,
Sir,
आगे बढ़े?
sir, a small question, sir.
Yeah.
So, sir, when we consider a particular condition, sir, for suppose we are in inversion layer and we consider a particular condition of specified VD and VD, I'm like VD and S, I'm sorry, VDS, and one gate voltage. So, can we claim that the whole velocity of these electrons in these, I'm like velocity saturation is at the same point, or the velocity of the all electrons in this channel which are present are at the same, I'm like same.
No.
Same.
No.
Okay, sir.
You cannot claim anything like that with electrons.
Hmm.
With electrons, you cannot even claim where the electron is if you know the Heisenberg's principle.
Okay, I'm like.
So all these are, again, I will repeat, these are models. So don't go about claiming such stuff. These are models to help you develop an understanding, a feel of the mechanisms.
Actually, sir, my doubt was that after some point, the pinch of.
Your voice is, I'm not able to hear you. Vaishnav, I'm not able to hear you. I'm sorry.
Hello?
Yeah.
Yeah, sir. So when the pinch off happens, sir, at that position, due to the high electric field, the velocity of the electrons is very high. So over there, sir, the velocity saturation again gets like decreased, right? Because the velocity of saturation is again, velocity of electrons is again speeding up at that position. But the position where I'm like at the source position, sir, charge density is high. That means that I would assume the velocity has been saturated. So doesn't this, I'm like, doesn't this make any kind of, because as we are saying that the current would be constant at some point after saturation, but there are two velocities, right, sir? I'm like, there is a velocity. I mean,
I don't want to answer this question.
Okay, sir. Sorry, sir. Thank you, sir.
No, I don't want to answer this question because if you start to go into such depth, then we can't even talk about DVD course actually. I would strongly recommend, please do SSD course, please do INE courses, because I see my role is to create that interest. My role is not to also satiate that hunger. Huh?
Okay, okay, sir. I do understand, sir. Yes.
Okay.
Thank you, sir.
Yeah. So let's move to today's class now. So we've looked at MOS capacitances, and we've looked at MOSFET also as a capacitance, where we said that the high frequency behavior and low frequency behavior of a MOSFET capacitance would be same. You remember this? We talked about this not just in the last class, but also in the office hours and at much length and in much detail. So why is that the case? Because there is a source and drain region, which is a cache of charges right next there. So if you need more electrons or holes, whatever you need, you will get them from that region. So even at very high frequency, the change in charge density would happen only in the inversion layer. But then this till now is about the gate capacitance. In reality, MOSFETs have many more capacitances. MOSFET transistors, yeah, MOSFET is a transistor. So MOSFETs have many more capacitances. Are you able to relate to this perspective view of a MOSFET?
Yes.
So where all do you think you will have capacitances when you look at this 3D structure?
So we'll have some overlap capacitances of gate and source, gate and drain.
Okay.
And then we will have some junction capacitances from source to body and from drain to body.
Okay.
And from gate to channel, there would be capacitances.
Gate to channel to MOSFET, MOS capacitance जो हमने देखी थी वही हो गई. Am I right?
Yes, sir.
Okay.
Sir,
are there any other capacitances here?
Wherever there is a change in medium, sir, I'm like, whenever there is a change in medium, then we would have some capacitance over there.
Okay.
So contact
Depletion
gate
capacitance.
capacitance will also be there.
Devajit दोबारा से contact and
Gate.
contact and polysilicon gate. Okay.
Yes.
Good. What else?
Depletion.
Mother?
The depletion capacitance when there is an inversion.
Yeah, depletion capacitances, we already, Gagandeep also mentioned that the source and drains will have their junctions and that junction would lead to capacitance. That is what you're talking about?
One capacitor, there is an inversion, this inversion is
Yeah, so gate to substrate capacitance we talked, we said that is the same as the MOS capacitance that we've already discussed at length.
It's apart from that, so there is one more capacitance, the inversion, entire body is the inversion.
Okay, so you're saying that there is another capacitance that appears from gate to body.
So from inversion to body.
From inversion to body, but that is the same medium.
So there is
How can there be a capacitance between inversion layer and the body? That is all silicon. Any charge needs to flow, it will flow.
There is a depletion between that, so in between inversion and body,
but
there is a depletion. So
depletion
there
is
a small capacitance.
But current flow can happen. So between inversion and the silicon body, there is no capacitance. Cannot be, because they are connected. Charge will flow. Charge flows.
I have seen in a diagram.
So if the inversion layer is not there, so don't get confused. If the inversion layer is not there, then we say that gate to silicon surface and silicon surface to edge of depletion, there are two capacitances in series.
Yes.
But at that point, there is no inversion layer. There cannot be a capacitance between inversion layer and the edge of the depletion region, because they are electrically connected. Okay. So yes, Meher?
Yeah, I mean, adding to Madhur's point, I didn't understand that if there can be a capacitance between your source and your substrate, because of the same reason, due to the existence of a depletion region, then why can't there be a capacitance between your inversion layer, which is
But
electron
source
rich?
and the substrate are different dopings. There is a depletion junction in between them.
Yeah. Okay.
If there is no inversion layer, then all the silicon is same doping. There is just depletion layer.
Right. But then how are we then differentiating your
How will you
inversion
get the
layer?
charges?
Because,
So, okay, for a capacitance, there need to be two plates
yes.
separated by a dielectric.
Yeah.
Where you could apply two independent voltages at two different plates, and then they are separated by a dielectric.
Yes, sir.
So if there is no inversion layer,
Okay.
where is the plate? And if there is an inversion layer, there is anyway a connection. There is a connection between that part of silicon and the depth. Akansha, you saying something?
I think she's unmuted by mistake.
Yeah.
Okay, sir. So, yeah, that I got, that when there's no inversion layer, just a depletion region. So effectively, there are capacitors in series. So the effect is that your capacitance gets lower.
Yes.
But so see, when there is an inversion layer, then the region of the substrate right beneath the plate acts like right between this right beneath the silicon dioxide acts as an n-type substrate, right? That's the
No,
point of an.
it is just a layer. It is just a sheet of electrons that starts to appear there.
Okay, so we cannot compare your source and drain with the inversion layer. They're two very different things.
Yes.
Okay.
Okay. So if we look at the top level view of the MOSFET, then this is how it would look. And that is the overlap region and the overlap capacitance that Gagandeep mentioned, that beneath the gate, there is an overlap capacitance. But in reality, let us say there is a contact over here. There will be a gate to contact capacitance, and there will be lines of electric field which would run between gate poly, vertical poly, and the active region, the diffusion region. So what does this mean? This essentially means that in a MOSFET, there is a capacitance CGB, gate and body. There is a capacitance between gate and source and gate and drain. And there is a capacitance between C source and body and drain and body. Are you able to appreciate all these capacitances?
Yes, sir.
Yes, Raghav?
So in the previous slide only, the previous one, sir, can you move there? So this electric field that you're talking about between the poly and the drain, which is coming out, I mean, the electric field should be in the overlapping region, right? But
why?
What is this?
Why just overlapping region?
So diffusion capacitances that you just the overlap capacitance that you talked about.
That is just one component of gate to drain capacitance. That is what I wanted to highlight. Gagandeep talked about just one component, which is the overlap capacitance. But there is this other component of capacitance between gate and drain, which would come with the gate to contact coupling and the gate to diffusion layer coupling.
So this diffusion layer coupling, I'm not able to get exactly what.
Exactly, yahi to dikhaya maine. There is a dielectric here. Let us remove this. This is all is dielectric. This is supposedly a metal equivalent because this is drain. There is this metal equivalent which is poly. So there are two metals. In between there is a dielectric. There will be lines of forces between them.
So what kind of dielectric will be in between this? I'm not.
Silicon dioxide.
So but that is the gate of, right? That is the gate one.
So everywhere is the silicon dioxide.
Okay.
But what do you think?
So we are covered.
What do you think? Is there nothing? Is there air between these two places?
I mean, I didn't had an idea about this.
So this all is silicon dioxide.
Okay.
We talked about oxidation, na?
Yeah. Okay. So we are covering every layer.
We talked about oxidation. See, Again, see, I am repeating the same thing again, which I repeated in the last session, that whatever we talked about, whether it was fabrication. So why do you think I'm answering all these questions, which supposedly should be answered in SSD and not in DVD? Why do you think I'm taking you through all this?
So you're trying to connect maybe different.
No, because you need to realize that unless you understand things from the very basics, you cannot become a good circuit designer also.
Okay.
Each one of those aspects that we have covered in the class till now, whether it was the design flow and hundreds of questions you asked around the design flow, or whether it was the fabrication flow and the so many questions you asked around the fabrication flow, or this band bending and everything. All of this you need to understand to be able to use transistors effectively and become a good circuit designer. This course is about circuit design. Therefore, these are the incoming inputs. अगर आपने courses नहीं करे हैं, then you need this kind of knowledge. Don't assume that it was an independent topic. सर ने तो BDF का introduction दे दिया था बस. No. I would rather not have given that introduction if it was not needed for this course.
Right, sir.
Okay.
So sir, this gate to drain capacitance in the model, that was consisting of this overlap and this also this
yes,
coupling, the other coupling.
The total CGD would have both components in it, the overlap capacitance and the gate, the polygate to metal and to contact and polygate to diffusion layer capacitance. Everything will be there in the total CGD.
So just one more thing, in the gate to drain, we are basically comprising 3 capacitances, right? So overlap, contact, and this above.
Diffusion layer, yes.
And same goes for the gate to source also.
Yes, gate to source. Similarly, gate to body. You know, in different regions. For example, if there is inversion layer, then the gate to body capacitance is something. But if your device is off, then the gate to body capacitance could be something else.
Yes, sir. That's the most capacitor.
Because the depletion layer would also come into picture there. So whatever components would come. When we say CGD, you should mentally or be able to relate, oh, all these 3 things would contribute to the capacitance. So if I tell you that, my friend, please reduce CGD, what would you do? As a designer, can you control this?
I don't think so, sir.
No, but as a designer, you can control the spacing between contact and this. As a designer, you can control the overall diffusion region. So as a designer, you can reduce the density of contacts. And therefore, you can control the poly to drain, poly to contact, or let us say gate to drain capacitance.
So what do you mean by the density of contact? This is mentioned.
We will see once we look at the layout.
Okay.
Abhi just park this.
Okay.
Okay, so this is the top. Let us abhi bhi dekh lete hain. So this is the top level view of the device.
Yes,
poly
sir.
and source and drain. So I can make multiple contacts over here.
Yes, sir.
So if I say that no, I will not make 2 contacts, I will make 1 contact. I will reduce the capacitance now, because I've reduced the area.
Right.
So that was what I meant by reducing the number of contacts. So as a designer, you can do this. So until you understand that all these 3 components exist, you will not be able to handle the requirements of the design effectively.
Okay. Right.
So do not think that this is only theory. There is a clear application of what we are talking about.
Okay. So sir, I can reduce the number of contacts. That is the between the 3 components. I only have one component which I can play with.
And I also said you can reduce the drain region, the drain area.
So drain area I can reduce now, because that is.
So if there is this device, I can say, oh, I will just make it this big. I will not extend drain unnecessarily.
So I mean, drain, as we made some layouts, it is dependent on the active region, right?
Yeah. So active region, you can keep it to the minimum width, no? Not just let it run hundreds of miles.
So, but that is basically controlled by the sizing that we have, that we want to achieve.
This
I mean,
extension I'm talking about.
okay. So I'm not
Okay.
I'm not aware of this parameter, right?
Yeah. So we will see. You will become aware pretty soon. You made the layouts now. In the assignment also you're making layouts.
Yes, sir. So, but
How are you not aware of this extension?
sir, I'm not controlling this because actually,
Why?
so I mean the width I'm controlling, so it is
Oh, you're
bigger.
using P cells to design your layouts.
Yes,
Am I
sir.
right? You're using P cells to design your layouts.
So no,
You're
I'm
you're invoking a PMOS and an NMOS directly.
yes, sir. Yeah.
Then you're automatically giving away the control that you would have had to the tool. Na? You make the layout by hand. Make the active region, make the poly. You will have all the control.
So right now, when we have done the schematic, then we do like generate from source and we get PMOS and MOS.
Don't do
And then
that.
we do.
So don't do that.
Okay.
Who said generate from source is the only way? Open a virtuoso window and make the active and make the poly.
Okay.
You have all the controls with you. आप खुद ही control दे रहे हो tool को आसानी के लिए. So how will you control? You're giving away a lever, a design lever.
Okay. Okay, so we can keep it to the like the minimum BRC that would enable it. Okay.
Yes.
Yeah.
So there
Okay.
are.
Yeah.
So you have two levers. You thought you had none.
Okay. Okay. So that will basically minimize that over that basically the coupling one, the gate to drain coupling. If we reduce this. Yeah.
Yes. See, the overlap you have no control over. Overlap capacitance is a technology feature.
Fabrication.
है ना? Because that is what is required to ensure there is some VT, some whatever. That you cannot control.
Okay, sir.
But whatever you can control, at least you should be aware of that.
Right. Right. Yes, sir. Okay.
You know?
Yes.
So this is how the gate and the various capacitances, you know, are kind of seen over here, where we say that the C gate is EOX by TOX into width of the device into length of the device. This is clear?
Sir?
Yes.
Sir, a small question, sir. So while you were mentioning about the pins on the drain and the gate, you said that there might be more than one pin. I'm like, why are we
Contact.
taking? Yeah, sorry, contact. My bad. So why are we taking more than one contact, sir? Actually, I'm like, firstly, why are we taking more than one contact, and why are we
So
again?
you do a P cell, you make a P cell, and make a device of width 2 microns. See how many contacts it will give you.
Yeah, sir. Actually, I've made that, but it has given many contacts, sir. I'm like, that was my doubt.
That is what I'm saying. Remove them.
I'm like, I should remove those.
Not all of them. Few of them.
You mean to say I have to connect them by each other or something, sir?
Remove them. What does remove mean? Does remove mean connect?
No, not as such, sir. Okay, sir.
Remove
I'll try.
means remove.
I'm like,
Instead of 10 contacts, use only 4 contacts. Use only what is needed.
Okay, sir. Okay. Thank you, sir. I'll try it.
Now, why are 4 needed? Why is 1 not sufficient?
Actually, that was my doubt, sir. I'm like, I didn't know why are we, I'm like specified about the number of contacts exactly. I'm like, why are we even I'm like looking into it exactly?
You tell me. What are contacts? They are kind of wires connecting the metal one with the source or the drain.
Yes, sir. Yes, sir.
So if you have 1 wire versus you have 4 wires in parallel, what happens?
Okay, resistance decreases. I don't. Got it, sir. Thank you, sir.
Okay. So what is being shown over here is that as VGS changes, there is a you can actually end up seeing different capacitance on the gate. Why is that?
So the above graph seems to be of the mouse capacitor itself. Right?
Yes. We've already done all of this. Okay. Above graph shows the depletion region being formed, and therefore the change of charges happening at the boundary of the depletion region. And as soon as the inversion layer comes, independent of frequency, we at once have high capacitance.
So what is this lower graph then?
These are the two components. This is the gate coupling with body, because depletion region was coming into picture. And as soon as the inversion layer is formed, there is no further coupling between body and gate. Now the additional charge comes from source and drain regions. Remember, in the inversion layer, we said that in devices, in MOSFETs, the source and drain will give the additional charge even at very high frequency.
Okay, so but in the lower frequency, when the inversion is forming, the charge is coming from the body itself, or is it and then also coming from source and drain?
You see, we've already shown it like this, that it is coming from source and drain. It is closer, na?
But it is showing that when VT has reached, I think so, then it's coming from source and drain.
So this is the VT point.
Right.
Great. So this line is the VT point. You see, already this capacitance has started to rise before that. What does that mean?
The charge, the inversion layer is forming due to the source and drain.
Yes.
So the lower graph is just basically elaborating that where that components.
They are components. This is component. There are various components. This is capacitance with bulk. This is capacitance with source. This is capacitance with drain. It's saying that all the three components add up to form CGC, gate capacitance. And source and drain, they have equal coupling because of equal overlap and equal density of charges there. Therefore, this is double. Overall CGC is double of CGS and CGD.
So, but this CGS is basically due to the overlap, right? Or is it also like all the three points?
अभी तो हमने बात करी, it is because of all three, ना?
Okay.
है ना? Vaishnav? Vaishnav, you have a question?
Sir, sorry, sir, I forgot to.
Rajneesh?
Sir, in this first graph, sir, here this gate to source and gate to drain, both are becoming, after this VGS is greater than VT, sir, they are becoming half. Sir, is this because of the uniform channel formation?
Yes, because VDS is kept at 0.
Okay, sir. Sir, after this, in this, sir, this saturation, nothing is told about this saturation in this.
That is the second graph. That is the graph on the right side.
So if we increase this VDS, so this VGS and VGD both will become 2/3 increased in the first graph.
No, due to pinch off, the drain will have no influence. Therefore, the gate to drain capacitance goes towards 0.
And this gate to source will become 2/3.
Will increase, yes.
Yes. Okay, sir.
Okay.
In the same graph.
Yeah, this one.
No, sir. In the left one.
In the left one, VDS is equal to 0. So there is no pinch off happening.
So suppose
both
at the
are
end
equal.
of So suppose at the end of this graph, in the first graph, we start increasing VDS. So then what will happen to VGS and
VGD? That is what we have done over here, na? We started introducing VDS. That is what happened.
So that's the continuation of it. Okay. Yes.
Yeah.
Yes.
यही तो है. Notice same points हैं. WL Cox by 2, WL Cox by 2. Same तो है. फर्क क्या है?
Yes. Okay.
Okay. Rajat.
Sir, in here we have written a C gate to be just depending on the thickness of the upside. So here it would actually depend on other factors also, no? Sir,
Yeah. That is where the graphs are there, na?
Yes, sir.
Meher?
Yeah, sir. This refers to before. So you told us about the three components. I got the contact capacitance and the coupling capacitance. That's fine, but didn't quite understand the diffusion layer capacitance you talked about.
We will come to that. We'll come to that.
Okay. And second question is, in this graph, you see we are seeing the components GCS, GCD, and GC bulk. But yeah, I mean, when we had studied the MOS capacitance, we were only, in a sense, I mean, from what I understood, we were only looking at the gate to bulk.
Because there was no source or drain there.
Yeah, but here we see that the gate to bulk capacitance keeps decreasing.
It vanishes. So it decreases for a MOS capacitance also. No? That is where we end up with the depletion region, where we go to WD max and we say this is the minimum capacitance you would have.
Yeah, but then it increases, right? But in this,
only in low frequency, when the change is happening in the inversion layer again.
But then, sir, I mean, even at high frequency, then after one point it remains constant.
But that is low. That is a low value.
That's low. But in this case, we just see it just keeps on decreasing until it vanishes. So
but
how
that
is that
the CGCB.
Okay, and
but because charges now start to come from source and drain region, therefore gate capacitance comes up.
Okay, so when you're talking about the bulk, you're talking about the substrate
only, the
not
substrate.
between inversion layer and gate.
No.
No. Okay. Okay, so
okay. So now we come to the diffusion capacitance. That was what you were asking. What is happening with the diffusion capacitance?
So can I?
You are explaining this?
No, no, sir. Sir, I want to ask about the rightwards graph, the graph on the right side. I was not able to understand that.
Yeah, tell me.
So here we were saying the GCD is decreasing and GCS is increasing. Why is that so, sir?
Because pinch off has happened. So yes, the drain is no longer connected to the inversion layer.
Okay.
The drain can no longer, so when you change the gate voltage, there is no longer any change in the charge towards the drain.
Yes, sir. That is why
CGD goes to 0.
Okay. And at the source side, we have a charge density. That is why it is increasing.
Yes. Okay. Now all the charge needs to come from the source side only. Therefore, the component or the value of CGCS increases.
Okay, sir.
Okay. But because pinch off has happened, the overall inversion layer width has reduced, or inversion layer availability has reduced. Therefore, the overall capacitance is reduced.
Okay.
Okay. So now coming to the diffusion capacitance. Are you able to see this tub over here? I'm calling this a tub because this actually looks like a bathtub or a tub for that matter. Which is where we have doped N+ for the source or drain region, let us say. Now, if I say that this is one plate, there is a PN junction on all the sides of this plate. Are you able to see this?
Yes, sir.
All the sides except this one. Why?
Because this is depletion layer.
Depletion तो इधर भी था.
So inversion layer.
Yes, because the channel is there. There's an inversion layer that we are talking about. Okay, if there was no inversion layer, then it would come on this side also. But in an on device, they say there is an inversion layer, so this will not appear. So if I want to find the capacitance of this drain or the source, what happens? I have to measure the capacitance on the side walls, and I have to measure the capacitance of the bottom of the tub. Are you able to see this?
So but the side walls is like on the side walls you have the dioxide, right?
Side walls, you have the, okay. So let us look at, wait. So side walls, you have this isolation, yes, but this is there, na?
Okay, sir. Yeah, didn't notice.
Okay.
Yeah.
Sir.
Yes.
So on the channel side, the inversion layer is just at the surface. But I have got that WD max, so that would also count now because it's not WD max is there, so I will get that.
See, on that side, even though there is a depletion layer, there is no other end of the plate because of the channel and the depletion layer. So let us look at it like this. Over here, so what are we saying? That there is a depletion layer over here, and then there is a depletion layer WD max over here, and then the source comes.
Yes, sir. Yeah, sir.
So where is the other plate now?
So the substrate itself will be the other plate, right?
That is too far away. In fact, there would be there is an easier way to flow charge from here from the inversion layer and so many places.
So is it like that? It is becoming like negligible kind of thing because of the too far.
That capacitance. So capacitance of this part of the plate to this part of the plate. It is such a big, long path. The dielectric thickness is so long. T oxygen T depth कह देते हैं. It's so big that the capacitance is insignificant in comparison to what you will see over here.
Okay. Okay.
Okay. So what do? We say that, okay, let us measure the perimeter and then multiply it with the number, which is C junction side wall. Okay. And let us measure the area, that is the extension and the width. Okay. So this is LS, the extension and the width. That will give me the area of the bottom rectangle, and I multiply that with C junction. And with this, I get the overall capacitance of the diffusion capacitance of the drain or the source region. Now again, if I want to reduce the drain or source capacitance, what do I need to do? Width is fixed, but I can reduce the LS. Are you able to see this?
Yes, sir.
So this diffusion capacitance is the gate to bulk, source, drain to bulk and the source to bulk. This is in the model.
Yeah.
And so one more thing, say in the junction capacitance of the like side walls, the way is this XJ parameter coming into picture, because it should also be there now for the parameters. We had it only 2LS plus W.
Yeah, so you will say that Cj into Xj becomes Cj as W.
Okay.
Okay. Because substrate तो वही है. You know the depth, and based on that, you came up with this value of Cj as W.
Okay. And so one more thing, so this LS component will have that overlap component also, right? Because that is there, right? Or it will be subtracted.
Yeah. LS would be the entire drain region, whether it is below the gate or not below the gate.
Okay.
If there is a junction existing there, so इसमें overlap की बात ही नहीं है राघव.
Yeah.
Overlap तो ऊपर वाले surface पे हो रहा है.
Right. Yeah. Yes.
Okay.
Sir, so you said that diffusion capacitance is a component of your gate to source or gate to drain capacitance, but in this case, it seems like it's a component of your source to bulk.
No. Oh. So I did not say diffusion capacitance. I said gate capacitance with the diffusion region.
Okay.
What I meant was those extra lines of this was, am I audible?
Yes, sir.
Yeah. This was gate capacitance with the diffusion region.
Okay, sir.
The diffusion capacitance, when we use the term diffusion capacitance, this is what is the diffusion capacitance that we're talking about. Okay.
Yeah. Yes.
So the diffusion term is coming because of the fabrication thing, right? Because we used to diffuse the layer.
Because initially the source and drain regions were diffused.
Okay.
That's why it is coming. Today they are implanted. Today the ion implantation is done. At an earlier point of time, phosphine was run through and diffusion happened. So that is why we called it diffusion layer. So purana naam chal raha hai. Okay. So now we come to the next component of our what do you say, VLSI devices, which is wires. And we've already talked about wires a little earlier, so we can be relatively quick now. So this is what wires are. What are they made of? We discussed this in much detail earlier.
Copper.
What are the wires made of?
Copper.
Copper or
Copper or?
copper. Aluminum, sir.
Yeah.
Depending on.
So in advanced technologies, they're always all fabs in advanced technologies use copper. In earlier technologies, let us say 180 nanometer and older, people use aluminium because the copper process was not as defined yet. However, today you will also find technologies which use 180 nanometers with copper. These are hybrid technologies to gain density or to have more current carrying capability and so on. But yes, what we are looking at is that these wires are made out of copper, which is more ductile than aluminium, and therefore these wires can be drawn very close to each other. We also know that these wires are like these cuboids. This is wire 1, this is wire 2. And when they run parallel to each other, this is the kind of 3D space they will create amongst themselves. So what happens? What all kinds of capacitances will you see here? So this is a metal running beneath. Let us say this is metal 1 and this is metal 2. So what all kind of capacitances will this wire 1 see?
So this will see a capacitance between the other wire in the same layer and with
due to
the
these
wires in
lines
the
of forces. Okay.
Yeah. And I'm assuming there will be another layer above these wires.
Okay. So there could be another wire running above it. So there would be lines of forces like this also. And
Similarly, so with the below layer.
and lines of forces like this. Are you able to see this? Your voice is not clear.
Sir, I am unable to picturize this, sir. So, how is it different, this M1 and wire 1? Can you please?
They are different metal layers, no?
Okay.
We saw the dual Damascene process.
Yes.
So what were we doing? We were making one metal layer, then we made vias and the second metal layer, then we made vias and the third metal layer. So these are these metal layers. The lowest plate is metal 1, then you have these wires in metal 2, then we have metal 3 up there.
Okay, sir. Yeah, got it.
Okay.
So, but metal 1 and different metals have been connected with Diana. So, like, then there is
Yeah,
the separation.
but suppose I am running a clock and I am running a data signal. Data signal is running in metal 1, clock is running in metal 2. Will I connect them also with a via?
No.
No, no.
Yeah.
There are two independent signals running in two different metals. What's the big deal?
Okay.
So we're talking over here as about two things. In this slide, we're talking about two things: width of the wires and the spacing between the wires. We're also talking about thickness, height of the wire, and the intermetal dielectric height, H. Okay. An important thing is, what is the ratio of thickness versus width of the wire? In old processes, wires were like this. So intermetal capacitances played a big role because of lines of forces. But in today's advanced technologies, wires are like this. So even if there is a metal layer running from above it, there are few lines of forces between them, but there are more lines of forces in the intrametal region. Are you able to see this? So what we are talking about essentially is that there are different components of capacitances, C top, C bot, and C adjacent. So in older technologies, C top and C bot were the dominating capacitances. But in advanced technologies of today, C adjacent is a very big component of the total capacitance. Okay. And if you want to look at how do these capacitances change as you bring the wires closer or something like that, you will notice that this is how it appears. So we have M1 and M3 planes there. Planes means there is a high density of wires there, and the spacing between my metal 2 wires is changing like this. So what do I observe? That when the width of the wire is less, let us look here. When the width of the wire is less, then an isolated wire would have this capacitance, whereas a dense structure of wires in metal 2 and metal 3 planes would have this capacitance. Now, if my wire width is very large, then adjacent capacitance does not change much. When I have isolated metal 2 wires, then the capacitance doesn't change much. But when I put metal 1 and metal 3 planes, because the width of my wire is large, this intermetal capacitance also starts to play a significant role.
So what do you mean by isolated? I mean isolated.
Isolated means no metal 1, metal 3 planes. Just metal 2 is there.
Okay, so we are looking at a plane, not between layers here in this graph.
Yeah, you may say so. जैसा यहाँ पे हमने दिखाया था, that this is a plane there. Shielding करा हमने, let us say. Okay, so what else can you deduce from here? If your wires, metal 2 wires, were very close, let us say 320 nanometer close, then the change in capacitance of wires, because of whether there is a metal plate up there or down there, doesn't really matter much. Are you able to see this?
No, sir.
So what does this hollow rhombus represent, according to you?
So I mean, S is the distance between the two wires in the same plane.
In the same plane.
Right.
So I am saying that two wires are very close. They're only 320 nanometers apart.
Yes, sir.
You see, if there was only single wire and no other wire, the wire capacitance would have been something like 60 or 70 attofarads per micron. When I brought other wires close to it, reduced the spacing, the capacitance has increased from that 60 to something like 230.
Okay. Right.
Now, when the wire was there was only single wire, because the spacing is infinity, means there is only single wire, and I put in the metal 1 and metal 3 planes, the capacitance increased from 60 to 130, more than doubled. But in a dense wire configuration, when I put the metal 1 and the metal 3 planes, the capacitance increased from 220 to only 230. Insignificant change. Are you able to see this?
Okay, so it means that at a very smaller, when we're going to very smaller dimensions, then the intermetal one is getting neglected.
Intrametal capacitance dominates.
In between the same layer, it is dominating, but
yes,
between layers is now okay.
Yes, and if you were using wide wires, then yes, intrametal also has some influence. See what happened? For very wide wires, the capacitance increased from 260 to 380. But if your wires are thin, which is usually the case, then there is not much impact of whether there is a wire running up there or not. That doesn't change the wire capacitance significantly. Are you able to see this?
Yes, sir. Yeah. Yes.
Okay. So let us look at how do these capacitances compare amongst each other. Typically, dense wires would have a capacitance of something like 0.2 femtofarads per micron, whereas a gate would have a capacitance of 1 to 2 femtofarad per micron. We discussed this in the last session. I had asked you if I have to implement a capacitance with gates or with metals, I prefer to implement a capacitor with gates. Why? Because it is much, much denser. You see, we put the numbers over here today. And we see that the diffusion capacitance is also very high. Why? Because over there also, there is only this PN junction. The dielectric thickness is very thin. Okay.
So what is this why diffusion capacitance coming here? So I'm not understanding.
No, we're just talking about different capacitive components as to why, what is the typical range of different capacitances that come into picture.
Okay, so in the earlier models, we are giving a number to the models.
Yeah. So we're just talking about this earlier model now. We're comparing the wire capacitance with the diffusion capacitance now.
Okay.
Okay, it has nothing to do with wire capacitance. We're just saying because you're now putting the numbers. I have not given you any numbers till now. No? First time I'm giving you some numbers so that you get a feel of what order we are talking about. Okay, so diffusion capacitance is actually comparable to gate capacitance, but diffusion is very resistive. So we do not, even if we have to make capacitances, we would not use diffusion as a medium to make those capacitances. Or even if I use a diffusion thing, I will put lots of contacts over it. I will put lots of wires over it, metal over it, so that the resistance reduces.
So this point I'm not able to understand. So avoid using diffusion runners for wires. What is this meaning, sir?
So let us say I have an inverter that is connected to, let us say, another. Okay. Sorry, I accidentally pressed end slideshow there. Kya karu? I have to restart then. Discard. Let me restart the slideshow. Yeah, you're able to see the slide again?
Yes, sir.
So let us say we have an inverter that is driving another inverter. What does that mean? That means there will be a PMOS and an NMOS, and the output of this PMOS and NMOS will go and connect to the poly of this other inverter. Something like this we want to do.
Yes,
what is
sir.
being said is you connected them through wires. Now don't go to diffusion layer and route through diffusion. Route only through metal. Now you will think, why would I want to route through diffusion? You may want to route through diffusion because there is the metal space is already occupied by some other metal there. There is some other signal that is running in metal 1. So you don't have metal 1 available. So you say, okay, let me go through diffusion and run it. You can't do that, but that is very resistive.
So I mean, what is routing to diffusion meaning here? I mean, reconnecting the metal 1 to the poly, that is diffusion you're talking.
No, routing means connecting these wires. This is routing.
Yes, sir. Yes, sir. This I understand.
So what is being said is don't use diffusion for routing purposes. Don't
So
use diffusion runners for in place of wires.
So what this mean? Yeah, diffusion runners. What is this diffusion runner?
Diffusion layer. I could just make a diffusion layer like this, and I would say I will see diffusion layer means active region, na? So current will flow through a diffusion layer also.
So
Right.
we are fusing to diffusion layers together. We are fusing to diffusion layers in this case.
I'm sorry.
So we are making those star diffusion layers as one diffusion layer.
Yeah.
Instead of
Don't use
connecting them
diffusion layers
together.
to connect. Don't use diffusion layers to connect signals.
So I
That
mean,
is the intent here.
so I mean, you're saying to be a don't connect the active regions in the layout.
No, no.
That you're
You have to connect the active regions, but connect them through metal.
okay. Just don't extend the active regions and connect like both the
Yes.
greens together, but connect
Don't
the
use
both.
diffusion layer in place of wires. Use
Okay, so
wires wherever possible.
so the green region in the layout we have to connect using the wires. You're talking.
Yes.
Okay.
Okay. So for very short wires, you can possibly use polysilicon at times, but avoid diffusion. Okay.
Okay, sir.
So one very important quick concept. So this we had already seen last time in the earlier thing. We had already seen that. So very quick concept I would want to give is that of sheet resistance. See, this H, as a designer, you have no control over it. Do you see that? This is a technology feature.
Yes, sir.
So the total resistance of a wire, in that, this rho over H is actually constant for you. Nahin?
Yes, sir. Height is not in the R control.
But your overall resistance then is only dependent on L by W, which we can say that L by W is equal to number of squares that I can make on this wire in the direction of flow of current. Are you able to see this? L by W has no dimension because L is also in micron, W is also in micron. So it has no dimension in itself. What does L by W represent? The number of squares that I can make or that I have to travel in the direction of flow of the current.
Yes, sir.
So what is the unit of sheet resistance then?
Ohms per meter square. Or
Ohm per square, not meter square. As many squares, that will be the resistance that will. So I will simply multiply sheet resistance with the number of squares and I will get the value of resistance. So if I have to flow currents in this direction, what will be the value of how many squares are there in this direction? Let us say this is the total length of the wire. How many squares in this direction?
2.
So I will get the value of 2 R naught. If I have to flow current in this direction, now what?
Sir, half.
R naught by 2.
R naught by 2. Okay.
Sir, we have to define a unit square also, right?
Unit square is always by defined by the width. Na? When I was moving current in this direction, the width was L. And the length for which I was running was W. So W by L is 1 by 2. That is where R naught by 2. When I'm moving in the other direction, when I'm moving in this direction, my width is W and length is L. So it becomes, and length is twice of W, therefore it becomes 2 R naught. Are you able to see this?
So what is this square concept you're talking about? Because we have wire, right? So we are talking why we are talking.
So what is the formula of resistance?
Rho L by A.
Rho L by A. That is what we have written over here.
Yeah, yes, sir.
What is A? The cross section through which the current is flowing.
Yeah, yes, sir.
So I said rho by H is R naught.
Rho by H is R naught.
Yeah.
So
what am I
H is
left with?
fixed. H is fixed.
Yeah, यहीं से तो हमने बात शुरू करी ना. For a given technology, H is fixed. Can you as a designer change H?
I'm sure, sir.
No. You make metal one. You have the flexibility to change the width of the wire.
Yes,
you
sir.
have the flexibility to change the length of the wire, Can you change the thickness of the wire when you're making a layout?
No, no, sir.
So that H is fixed for a given technology, is it not?
Yeah, yeah. Yes.
That is what we are calling as R0.
Okay.
Now, what do I multiply R0 with to get the value of resistance? The number of squares that have to be traversed. This ratio is the number of squares.
Okay.
Okay. So I think we are already on time now. So this also we'd already seen earlier. So we will not look into this again. You even had a question in your quiz on this topic. We can probably talk about polishing, but that we can do later also sometime. So we'll talk about these models in the next class. Okay.
Sir,
Yes, yes, Krishna.
sir, can I say something about the assignment?
Yes, please.
So currently, some of us are not having VNC access, and also they have a server is not working from yesterday, and also they have told not to use MOBA until we are getting the VNC access. Since they won't be able to provide VNC if we are using like MOBA in parallel, something like that. They have told now, and so currently we are not having like anything to work on for the assignment.
So raise a flag with the TAs. This thing should be resolved, because it is not about assignment के लिए है कि नहीं है. Finally, for the project, you will need all this access. So
yes,
the purpose of this first assignment is so that you can pipe clean all these things for you, so that when you run you get hands-on, you get a good handle on the tools. That is the purpose of this first assignment. So just get this thing resolved for yourselves. It's very important. Talk to the TAs, get this thing resolved.
Okay, sir.
Okay. The TAs are very willing. They are very willing to help. So don't hesitate to reach out to them. Okay. So I'm stopping the recording now. Yes, Madhur.
I have a question on wire connection. So you said that we were instead of running wires, the plane we were running the vertically to reduce the capacitance. So I didn't understand how we are connecting jumps by running the vertically.
So Madhur, your voice is actually बहुत illegible नहीं कह सकते, but I'm not able to understand exactly what you're speaking. There's lots of echo, I think. पता नहीं, कुछ तो गड़बड़ है. I'm not able to hear you properly. Are others able to hear him properly?
Not at all, sir.
No, sir.
It's not just my setup then. Okay. You want to write the question down on the chat window? I'm sorry. So I'm stopping the recording for now. If Madhur is putting his question there, then